sort of able to talk after Andrea Cavarera. Density, BEC-BCS crossover, and photo-excited transient superconductivity. So this is about the role of competing state and understanding what's going on with some model. So unconventional superconductors, we fortunately find in many of these new superconductors. And most notable thing is that there are definite non-BCS-like condensation that is suggested by the 4 different phenomena. So the first one is TC scales with the superfluid density. This is something we did with MUSR since the very early days. Second is pseudo gap behavior T star, this measured by NMR transport and RPES later. Third, non-BCS-like feature is the vortex-like Nernst effect and diamagnetic susceptibility that is pioneered by Huang Ong. And the fourth one is just introduced by Andrea, that he found a very nice transient superconducting-like response after photoexcitation with very high apparent transient TC. So I wish to connect all these phenomena and if possible propose a phenomenology based on equilibrium and transient superfluid density and discuss the role of competing antiferromagnetic versus superconducting orders. And that is also appearing in neutron magnetic resonance mode and optical 400 Kaiser mode. So we started the study of high TC cuplet superconductor by MUSR by measuring the magnetic field penetration depth 1 over lambda squared that is corresponding to the superfluid density NS over M star. So what I'm plotting here is the transition temperature in the vertical axis and the lowest temperature approximate value of the superfluid density determined by MUSR penetration depths. And so these are each different specimens, and this is 214, 123, and 2223. And especially in the underdoped region with increasing doping, we found that TC is following nearly linear relationship with the superfluid density. And that was one of the first definite indication of the condensation is not BCS-like, because if you have BCS superconductor, the TC is determined by the energy gap delta, and superfluid density is essentially all the carriers in the sphere, as long as this Fermi-sphere is protected by an energy gap, even a small gap. So let's say if you have this black gap, and then you can somehow reduce the gap size to the half, your TC will become half, but the superfluid density will stay the same. So this means that for BCS-like condensation, you would not expect much of correlations between TC and the superfluid density. Instead, we are seeing very strong correlation here. And so in my opinion, so this is one of the first indication of non-BCS-like behavior. Okay, then we added many data, as perhaps you know, on different unconventional superconductors doing the similar measurement. And here we show the results of iron arsenide and buckyball superconductor potassium 3 or other alkali 3C60 here. And also the overdoped side of the cuprets. So in all these cases, we see approximate linear correlation between TC and the superfluid density, which is quite interesting. But the simplest thing we can do is to now we are doing the measurement to decide N over M star. And so if you have the information of M star, you can essentially calculate how many carriers you have. And if you have the coherence ranks, then you can say that how the spatially pairs are overlapping. And if you do so in the BCS superconductors, you have many, many pairs overlapping with each other, as you know. In the case of typical Bose-Einstein-like condensation-like system, helium, you have nearly independent bosons touching barely with each other. So most of these new superconductors following this linear line seems to be having about several pairs overlapping with each other. So this is not only the relationship, but the number-wise, this situation is very close to the Bose-Einstein condensation situation, but essentially interpolating the cases of BCS and BEC. Okay, so then we made this a little bit more quantitative by obtaining energy scale, which I call the effective Fermi temperature by using the number density of carrier and mass we estimated from superfluid density. And so this is a plot of that. And these are cuprettes and buckyballs, and so the unconventional superconductors. They have very high TC with respect to this effective Fermi temperature or Drude spectral weight temperature. And as compared to that, and the linear line I showed corresponds to this line, but as compared to that, the BCS superconductors, they have very high Fermi temperature, but rather small TC. And also the Fermi temperature, for example, they are about the same for tin and aluminum and zinc, but TC is different. So there's no correlation between Fermi temperature and TC. So as I mentioned earlier. Now, another thing we can do is, of course, since we obtain the number density of carrier and mass, we can think if these fermions are subject to very strong coupling and form very ideal Bose gas, what would be their Bose condensation temperature? And that Bose condensation temperature is shown by this red dotted line. So if there are preformed pairs, and then this red line corresponds to the situation that you have each boson at very high temperature has very small thermal wavelengths. So they are behaving like classical particle with independent from each other. But if you cool down at this red line temperature, so the thermal wavelengths of a boson becomes comparable to the interboson distance. And then these bosons would like to make phase coherence. And then this is the point where they would start to condense, make Bose condensation if there's no prohibiting or against factors. So for this is ideal case. So this is actually so hypothetical and idealized case. And as compared to this idealized case, the actual TC of these existing superconductors are reduced by about a factor of 5. And that is very important thing. I will discuss that later. But anyway, so up to this point, my discussion for this TB line is just this is a hypothetical essential calculation and hypothetical situational line. But I hope to show you today that some of the measured quantities, actual measured quantities, actually follow this line. And so first of all, first of them is the vortex Nernst effect onset temperature. So in 2000 and about 10 years from that time, Juan On has pioneered measuring the vortex Nernst effect. And for example, this is RSCO, and this is the onset temperature of the vortex Nernst effect. The real TC is here, okay? It's much lower temperature. And for example, in the underdoped region, there's about a factor of 4 or 5 difference between the onset temperature of Nernst effect and real TC. So the same interesting thing happens also in the diamagnetic response. And again, this response onset temperature is about the same and about factor of 4 higher than TC. So this factor of 4 or 5 higher than TC, then if we would like to plot the Nernst onset temperature, for example, for this particular cupret, you can just use the μSR measured superfluid density for the horizontal axis and the onset temperature of the Nernst effect for the vertical axis. And if you do so, the point for underdoped 214 is one of the point is here. You can also plot a point for underdoped 1 to 3, and it becomes here. And also, as Andrea mentioned, the Nernst effect was measured on BEDT organic superconductor, and the highest onset temperature of that Nernst effect is here. And also, if you look at the Nernst onset temperature, for example, uranium to silicon, to the point is here. So we have at least 4 actual examples of this hypothetical Bose-Einstein condensation line seems to be observed as the onset temperature of the Nernst effect. Okay, so another phenomena which actually plots the point on that line is this Andrea's experiment of photo-induced superconductivity. So as he mentioned, if you excite the system by light, the photo-excited case, even at 100 Kelvin, this potassium 3C60 shows this missing Drude spectral weight, which is a characteristic of superconducting-like response, as you can see here in the equilibrium case. So from this missing spectral weight, we can obtain transient superfluid density. And also, this phenomena has transient onset temperature. And so based on that transient superfluid density and transient onset temperature, potassium 3C60 equilibrium superfluid density would give you here, but the transient superfluid density and onset temperature would give a point for the Cavaleri's effect onset here, which is actually very close to this dotted line of hypothetical BEC line. And okay, so as we will show you later, but one of the 1, 2, 3 YBCO system also puts a point here. So this transient effect is also seemingly very much related to this dotted line. Okay, so let us see the phase diagram. So potassium 3C60 or alkaline 3C60, this is a phase diagram. You have an antiferromantic region and then superconducting region, which depends on the lattice constant or pressure. And we measured mu-SR, by mu-SR, the superfluid density. And if you have the superfluid density, you can calculate this hypothetical Bose-Einstein condensation, ideal Bose-Einstein condensation temperature. And for example, potassium 360 has a point here. And Andrea measured the transient superfluid density, and it has a little bit more spectral weight than the equilibrium spectral weight. So for example, for potassium 3C60, from this little bit more of the spectral weight, we would expect that the hypothetical Bose-Einstein condensation to take place at this temperature. And you can compare with the real onset temperature. It is not quite easy to estimate, but something like this region would be approximately right for the onset temperature. And so in this way, we can say that this phenomena has an onset temperature which is consistent with that predicted from this argument of hypothetical Bose-Einstein condensation point. As also he mentioned just now, that if you apply pressure, this phenomena is reduced in temperature and goes away very quickly. So this is how it disappears. And I will show you soon that this is very similar to the case of Nernst effect. Okay, so up to now, actually, Andrea visited Columbia in 2017, and I was sitting in his lecture, and immediately at that time, I thought that we can plot his data in this way onto this my plot. And then also at that time, I was also realizing the connection with the Nernst effect. And so actually I suggested him to explore this BEDT system. And now we are very happy that he did experiment. But the BEDT system, again, the phase diagram is shown here. And you have superconducting state. And we measured superfluid density by mu-SR and other technique, and it is giving this hypothetical BEC-like temperature scale. And the Nernst effect is happening here, but again, it is quite rapidly reduced in the overdoped region. So this is the trajectory of Nernst onset temperature. And Andrea did his measurement, and as you probably heard, his onset temperature is about 60 Kelvin. And so this is the Andrea's phenomena point. And it is, again, very close to this hypothetical Bose-Einstein condensation, right? Okay, so this gives our sort of photo-induced point here for the BEDT superconductor. Of course, as you can see, not all the points, all the Nernst point or photo-induced point would come onto this line. For example, this overdoped thing, which is where these phenomena that dying away would give points, not here, but reduced onset temperature. Okay. Now, probably the most interesting thing is to see what's happening in the case of cuprets. And so this is the phase diagram of the cuprets. And firstly, I showed Nernst effect onset temperature and diamagnetism onset temperature here. And this is actual TC. And this is the T star, which would probably meaning pair formation or boson formation. And obviously, first of all, this Nernst effect onset is much, much lower in temperature than this T star. Okay, that's a very important thing to realize first. And the underdoped side of this Nernst onset temperature is, as I showed you, following this hypothetical BEC line. Okay, and but this hypothetical BEC temperature was calculated from the zero temperature superfluid, and we are not necessarily sort of distinguishing if this comes from preformed boson condensation or fermion condensation. And but this Nernst effect seems to be responding to the condensation of or related to only preformed pair. And if you assume that, then T star is coming down. So in this region, near optimal doping, the number of bosons are very much restricted by this coming down T star. And because of that, this this hypothetical Bose-Einstein temperature is coming down because boson's number is reduced. And it will show this trajectory. And so phenomenologically, we can probably interpret this as showing that that this Nernst effect is appearing when at least local phase coherence is achieved among preformed bosons. And that's why this is coming down close to this T star line. And actual TC, as I always mentioned, is reduced by a factor of 4 or something in the underdoped side, and still reduced even in this optimally doped region. Now, so where is the point from this transient effect of Cavallari group? And this Andrea could probably correct me if I'm wrong, but he did several experiments on the 214 systems. And this is case of RESCO, and which is actually not quite superconducting without right excitation in the concentration of this particular concentration. You have charge order, spin order, and so on. But application of the laser light somehow melted this stripe order and generated, I think this is the reflectivity edge. And so this is sort of superconducting like response. And this is going up to something like 80 Kelvin. Similarly, LBCO, some of the transient effect was seen up to something like 60 or 80 Kelvin, 60 Kelvin. So if we assume that the carrier density of these systems are more or less the same as this 0.125 like carrier density in LSCO, then we can plot the onset of this transient effect, and it comes something like here. And so I think this depends very much on the power of laser and various details. So this is not necessarily be exactly compared to the nearest onset or this line, but I think this is probably telling that this transient phenomena is setting on along this line and not with the very high temperature of the T star line. So just after the discovery of cuprates in the early 1990s, I was trying to advocate this picture of Bose-Einstein to BEC-BCS crossover. And at this time, we were not assuming necessarily the effect of competing order or so on. So we had this pair formation, maybe mimicking T star, and we just wait to cool down. And if the number density situation of this thermal wavelengths and inter-boson distance would be satisfied, we expected the condensation to happen. But the reality is now clear that between this line and the actual TC line, there's another line, very important, another line here. And that is because TC line is actually reduced from the idealized Bose line. And this is as shown here, it is reduced. And so the reduction is very important for us to understand. Okay, so why is TC reduced from this hypothetical or idealized Bose-Einstein situation? And this, I think we can learn from comparison with superfluid helium, because superfluid helium, this idealized Bose condensation should have happened at 3.2 Kelvin, but the lambda point is 2.2 Kelvin. So this is 50% reduction. And as I also mentioned already, that cuprates, we see that TC is reduced by a factor of 5 or something. And so let us see what is the case of superfluid helium. And this is the phonon-roton excitation spectrum. And this is the roton minimum. And this is the Bragg point of competing order helium. Helium has hexagonal close packing solid order as a competing order. So if you see this, the Bose condensation temperature idealized as 3.2 Kelvin becomes real 2.2 Kelvin. In my opinion, it is reduced because you have excitable mode here. Okay, so TC usually have to be explained by some existence of mode or spin wave or whatever. And so this mode is very important to determine T lambda point, in my opinion. And so, but this, rotons are kind of short time, short range correlation of the solid like correlation, which is floating around in a sense in superfluid. Okay, and that excitability is very important. And to convince you that TC, this is a lambda point, like so, and this is roton energy, and they are linearly correlated. And the ambient pressure is here, you apply pressure, and finally helium solidifies soon. So we have only a small region of linearity, but this is showing, in my opinion, that that the bosonic superfluid helium-4, three-dimensional helium-4, the TC is related at least and maybe determined or dominated by the soft mode energy related to the competing order. Okay. So we can extend this analogy and see that the resonance, in the case of cuprates, resonance mode is a good candidate for the role of rotons, like rotons. And in fact, you see, if you plot resonance mode energy versus TC with the same aspect ratio, then you have this, and the ratio is about the same as the ratio of this rotons. And moreover, as you know, this resonance mode has a hourglass shape. And what is important here is the smallest energy excitable mode, and that is called spin gap in the case of cuprates. And if you plot the spin gap energy and the onset temperature Tc, then the ratio is almost exactly the same as that of the rotons. So that is not only for the case of cuprate. This is a logarithmic plot of Tc versus mode energy, and these are this spin gap energy of the cuprates. But we also plot the various resonance mode energy for, ion doped, ion based, and ion selenide. This is the heavy fermion, cerium kappa to silicon 2, and helium roton with various pressure is shown here. So they have almost exactly the same ratio. And so in my opinion, this is suggesting that thermodynamically, probably this excitable mode of the competing state is determining Tc. In fact, actually, so the resonance mode is appearing in the periodicity of competing anti-ferromantic order. This is very similar to the rotons appearing in the periodicity of the H solid. And in the free energy diagram, so there are two competing states. And the resonance mode-like energy is, I think, corresponding to the difference between these two states. And if, for example, magnetic order wins, then this energy comes down, and resonance mode, the spin gap is closed, right? So spin gap is representing this free energy difference. And this situation, in fact, can be seen in this phase diagram. These are the phase diagrams of the various unconventional superconductors, but this end helium, superfluid helium. What is very important is that this boundary is almost always first order, right? As probably you know. And that is very well sort of consistent with this behavior of the free energy. Okay, so this is a Bose-Einstein BEC-like crossover picture. And this magnetic resonance mode actually is well known to be D-wave superconductor response in the case of optimal and overdoped case. In that case, your final state of exciting condensate is, so you excite bosons, but it is becoming E. And so this is a pair breaking interaction, excitation. And this is exactly what the usual people would love to say about D-wave. However, if we consider this underdoped side, rather deep underdoped side, most of your normal state is 2E. And so then you excite this boson to another boson in the normal state. And that should be the process to determine thermodynamically the Tc. And so for this pair non-breaking excitation, I think this resonance mode is a very good candidate. And so this is another type of thermal pair breaking excitation. Many people say that phase fluctuation in two-dimensional Koster-Saurus is pair breaking, a pair non-breaking fluctuations, but this is different. This also occurs in 3D. And that is, in my opinion, necessary. Something like this is necessary to account for the thermodynamic transition. So in my opinion, this magnetic resonance mode has a dual character or additive character of this pair non-breaking like situation and pair breaking, usual pair breaking like situation over the evolution of in this phase diagram. Okay. Now, so this is the this stripes and its spin charge kind of correlated order. And Andrea again was able to melt this spin charge order by light excitation. This is how the Bragg peak of that stripe is perturbed by the light. And he showed that that laser excitation induces this reflectivity, superconducting-like response in a short time. Okay, so this is already showing that what light is doing is essentially killing competing antiferromagnetic or stripe order and helping superconducting order. Now let us see the case of YBCO. This is kind of controversial, and so I left it up to here. Now, firstly, the Nernst effect and diamagnetic susceptibility was reported, and it is showing very similar situation as the case of ALSCO. Nernst effect reported by Taillefer's group is including K-psi particle response, and it is therefore following more or less like this T-star line. Okay. Now, so Andrea's experiment was published in YBCO's different concentrations. And essentially, he's able to measure this superfluid density, transient superfluid density in various YBCO systems. And this circle is the equilibrium superfluid density. So for the case of the 6.6, the superfluid density onset temperature is something like 150 or 200, and the superfluid density is small. And anyway, so this onset gives a point here. For this 6.5, the superfluid density is actually somehow similar to the equilibrium value, so we can actually plot with μSR superfluid density. And the onset temperature is something like 300 or 350 or something, and it gives, therefore, the point here. And this point could be interpreted in both ways. If you like, this is still close to the following, this hypothetical Bose-Einstein condensation line or local phase coherence line, but it could be following this pair formation line T star. And then you can go to this lower concentration, more underdoped YBCO. And okay, so onset temperature is rather high, but the superfluid density is very, very small. But in, for example, 6.3, in the equilibrium, this material is not superconducting, but somehow light at least induce some of the carriers. And so in this kind of cases, light excitation could also not only killing the competitor, but also maybe inducing additional carriers. And it is somehow complicated in my opinion. Nevertheless, so Andrea just plotted, their publication plotted this onset temperature. And if you just do that against nominal concentration, then you will see that that onset temperature follows T star. In this case, therefore, boson formation temperature. And this story is somehow different from what I try to advocate up to now, that this phenomena should be following this local phase coherence buildup. Because boson formation is two-body problem. You just need attractive interaction. This local phase coherence is a many-body problem. You have to count the number of carriers. Anyway, so this is a difference. Still, I think this interpretation difference and so on exists between myself and Andrea's group. And so YBCO is kind of still complicated in my opinion. But there is something which could clarify or guide us. And this is a very nice experiment published earlier on equilibrium usual measurement of optical conductivity and by Christian Bernhardt's group. And what is often very important for optical conductivity, there is something like 400 inverse centimeter. There is a mode which with this optical conductivity changes as a function temperature in the superconducting YBCO. And so this black line is the temperature evolution of the so-called 400 Kaiser mode. And the spectral density is increased in the superconducting state. And but if you heat up, that spectral density goes to this phonon mode. And phonon mode also changes the frequency. So these two phenomena occurs at around 180 Kelvin, and this is much lower in temperature than the T star, the boson formation temperature. And so in the phase diagram, this 400 Kaiser mode onset gives the trajectory here, and that is exactly the trajectory of local phase coherence or Nernst onset effect, as I showed in the case of 2 and 4 cuplets. This is the 1, 2, 3 cuplets from optical measurement. So this 400 Kaiser mode, I think, is very important. And now this is sort of unaccepted. My own toy model sort of speculation for what 400 Kaiser mode could be. Now, 400 Kaiser mode was studied very well as a plasma mode for this adjacent plane of coupled oxygen plane in YBCO. But my amateuristic thinking is the following. So this magnetic resonance mode, you measure not only by neutrons, but you can measure by Raman, A1G. And if this were spin-alone mode, then Raman should be twice in energy as spin, because as you know, 2 magnon Raman mode. But here we are seeing 1 magnon is corresponding to 1 spin excitation. And this is very special situation in my opinion. And I think this is coming from this is a stripe order, and you make this stripe as fluctuations, but I think you have to assume that spin fluctuation and charge fluctuation are hand in hand taking place together. And if so, if you would expect that this dispersion relation, spin excitation exists here with 41 millivolt at the position of the stripe satellite stripe magnetic peak. But I think corresponding to that, the charge excitation may be here. This was not easy to observe, but with the same energy. And if you assume that this is something like 400 centimeter inverse, and in fact, Tom Timsk noticed early days that the intensity of this magnetic resonance mode, this is spin soft mode, goes almost identical to this 400 Kaiser mode. If we assume that 400 Kaiser mode is somehow can be viewed as a charge soft mode, this is just showing how charge and spin are directly related with each other and fluctuating together. Okay. So by looking at that, we can see the Andreas data of time dependence. This is a case of how the light excitation changes this 400 Kaiser mode. It actually eliminates the 400 Kaiser mode for some time, and it comes back, and then everything comes back to normal. So, okay, so what light does is to put the spectral weight to lower frequency or lower just to this phonon-like mode. And this is more the same as the if you have high temperature, you would achieve. And so this is quite just hypothetical, but the light is suppressing 400 Kaiser mode. And I showed you that 400 Kaiser mode may be viewed as something representing also magnetic resonance mode or the soft mode, charge spin soft mode. Then removing that means that removing your competitor, and then that may help transient promotion of superconductivity to higher transition temperature, because the existence of the competitor that is measured by the resonance mode or maybe 400 Kaiser mode is reducing TC. Okay, so what I showed you that effect of photoexcitation and LBCO and LESCO, it's easier to understand. The right, Andrea was melting charge and spin stripe order and helping superconductivity. In the case of YBCO, in my opinion, they are melting resonance mode or 400 Kaiser mode that is a inelastic mode. of competing order, and that is still helping inducing higher TC of transient superconductivity. So finally, if you could allow me to go on 2 more slides, recently there has been a measurement of bilayer and trilayer twisted magic angle graphene, and Pablo's group and Philip Kim's group measured this phase diagram and onset of the tri-layer graphene in this case. And so the temperature dependence of the conductivity behaves just as you expect from this Koster-Retsaurus transition. And for this particular single layer system, somehow they found that at highest TC case, this BKT, this is onset temperature of superconductivity, is corresponding to 2-dimensional Fermi temperature. This Fermi temperature was reduced by normal state carrier density, gate carrier density, and normal state effective mass. So it may not be corresponding directly to the superfluid density derived TF, but this is what they found. And somehow this is interesting, but quite odd, in a sense that for any strong coupling or weak coupling superconductor, if you make it very thin, the Koster-Retsaurus theory would dictate that transition should be 1/8 of the Fermi energy scale. And this is happening in this sense only in this particular gate value. Similarly, Iwasa's group recently published this 2-dimensional Bose-Einstein BCS crossover-like interpretation for this single layer zirconium nitride chloride and with lithium, and that is gate tuned. And in some range, so their Fermi temperature and the onset temperature of the superconducting-like behavior agrees well, just like in the case of the tri-layer graphene. But then he is doping more and more carriers, and at least n over m star would behave this way. And so this is, again, I shall caution you, this is coming from normal state Fermi temperature estimate. But this trajectory is completely different from all other 3-dimensional unconventional superconductors. So we have now new thing to understand and explain from single layer system in a few example cases. Finally, this is my last graph. We have been showing mostly this highest TC case, but there are many systems somehow showing this nearly linear relationship, but with much higher superfluid density. And for example, transition metal dichlorocogenide with various pressure, iron selenide sulfide is here. And many materials show this sort of linear relationship. And so this, I think, is not coincidence, but there should be some fundamental reason. And one of the reasons may be that, this system, for example, has a multi-band effect. And so it is encouraging us to think about why so many sort of systems just show this linear relationship. Okay, so I'm sorry for overtime, but this is my conclusion. So I showed first attempt to explain onset temperature for both of the vortex nanostate effect and photo-induced transition, transient optical responses, and onset occurs at, in my opinion, development of local phase coherence among preformed bosonic charges. And I showed that the role of competing antiferrometric order in controlling global phase coherence and the superconducting transition. And photoexcitation seems to change the balance between superconducting and antiferrometric competition. And by temporarily killing or suppressing antiferrometric order. And I showed you also magnetic resonance mode and 400 Kaiser charge mode. Especially today, I said something new, and that is the way to view 400 Kaiser mode as a charge soft mode, similarly to magnetic resonance mode being viewed as spin soft mode. Thank you very much.